Hello and welcome back to PC Retro Tech. So a recent video of mine on the channel on the ATI VGA card with a coprocessor seemed to pique quite a bit of interest amongst you guys. So I thought I'd continue on in that vein, looking at other old video cards and standards. This is an original IBM CGA card from 1981, and it was what was used in the Area 5150 demo that was released late last year for the IBM PC and XT, which I was also involved with. Now, the real king of reverse engineering the hardware of these cards, as far as I'm concerned, on the PC is Reenigne, a member of that group. He and Weiler, the graphical artist for that group, did a lot of work on register writes to the CRT controller chip that's used on this card. And between them, they came up with lots of really amazing graphical effects, which you can see in that demo. But there's still a lot that we don't know about these chips. There's two that I commonly see on this card, the original Motorola MC6845 and a Hitachi clone of that, which is used here, the HD6845. And on other similar era CGA cards, you'll also find a UM6845. But there are rumours amongst other communities that use these, for example the BBC Micro and the Amstrad CPC 464 communities, that you can get even finer control by register writes of this chip down to the cycle accurate level. And maybe you can even get control down to a partial character level, which I'll explain the importance of a little later in the video. So some people reverse engineer these by delidding them and taking photographs and working that way, but I want to non-destructively reverse engineer this. See if we can come up with any glitches that could be used in a future demo. First of all, how does the CRT controller chip actually work? It's just a character device for displaying text mode. It has a register for the number of characters across and another one for the number down the screen. And actually the CGA card can run it at two different speeds. One's fast enough to get 80 characters across and the other one only 40. And in both cases you'll get 25 characters down the screen. So those are the parameters that we normally put in those registers for CGA text modes. But we know that the CGA card can also do graphics. The CRT controller chip has no idea about graphics, so somehow the CGA card uses this character device to also display graphics modes, and I'll explain how that works in a moment. For the text modes, the CRT controller chip is outputting a character address which gets incremented for each character position on the screen. It gets to the end of the first character row, and when it starts the next character row, it just continues to increment that character address all the way to the bottom of the screen. Now, of course, the CGA card uses that character address as a lookup into video RAM. And it's in video RAM where we specify which characters should be in each position on the screen. And this is done using ASCII codes. So each of these is a byte, so there'll be one ASCII code byte for the F, then another byte for I, then an L, and so on in video RAM. And of course these ASCII codes don't tell the CGA card which pixels to display, just which character to display. The pixel information comes from another chip called the character ROM, which, if you like, has little pictures of all of the characters in it, and with all the pixel information that the CGA card should display for that character. Now, of course, the monitor doesn't display all the scan lines of the F, then move on and do all the scan lines of the I, and so on. We know that the monitor just displays one scan line right across the screen at a time. So it actually has to display multiple scan lines per character row. And to that end, the CRT controller chip actually has to output the same character addresses multiple times in a row, one for each scan line of the character row. Now, there's a little register in the CRT controller which specifies the number of scan lines per character row, and for CGA characters this is 8, and so that's the value we normally put in that register. They're 8 pixels high. And it basically outputs not just a character address, but also a row address. So that row address specifies which scan line of the character row we're currently on. And so basically the way it works is the character address is used to look up a position in video RAM. It gets the character code and it gets the attribute byte from video RAM. the ASCII code is used to look up in video ROM which pixel information should be displayed, and it figures out which scan line of that character it should be displaying using the row address, which will be 0 to 7 on CGA text modes. So that's how the text modes work. How do the graphics modes work? Well, one way of doing it, of course, would just be to forget the character ROM entirely and just put the pixel information directly into video RAM, and that's exactly what they do. So there's still 2 bytes for each character position, and those 2 bytes can fit 8 pixels. In the 4-color graphics mode, you need 2 bits per pixel, since there's only 4 colors, 0, 1, 2 and 3, and you'll manage to fit 8 of those into each 2-byte location. And the other complication, of course, is that there are multiple scan lines per character row, and the CRT controller chip doesn't know any different. So one way of fixing that would just be to tell it, I only want 1 scan line per character row, and that would mean that it'd get to the end of just 1 scan line, decide that it's done with that entire character row, and then go on to the next character row and so on. So you get unique information for each scan line on the screen. Unfortunately, a little limitation of the CRT controller chip made it impossible to do that. So they actually had to use 2 scan lines per character row in graphics mode. So you actually have 100 characters down the screen, each of which is 2 scan lines high in graphics mode. And in order to not duplicate the same pixel information for each of the 2 scan lines of a character row, what they do is they use the row address, which is now alternating 0, 1, 0, 1, 0, 1 all the way down the screen. They use that row address to select a bank of video memory. So there are 2 separate banks, bank 0 and bank 1. And the row address is used to switch between those. They're just alternating banks all the way down. And so that means that you'll get unique information for each scan line on the screen. Between the character address and the row address, you'll get a different location in video RAM. And so that's how graphics modes work on CGA. Now, it turns out that I haven't shown you everything here. I've just covered the active portion of the screen, the part where it's taking pixel information from video RAM and displaying it on the monitor. It's 40 characters wide in graphics mode, as we know, and 100 characters in the vertical direction. But there are other portions of the screen as well, the border regions, for example, and I've shown those here in grey. Now, you might imagine that the border goes equally all around the active region, and certainly when you look at the screen, that's what you see, but the CRT controller chip actually has a different view of the world. It starts its run at the top left of the active portion. It displays characters. There'll be 40 characters or 80 bytes, which is 320 pixels, and then it starts the right-hand border of the screen. And this is done in the background color, whatever that currently is. And then I'll just put this in. And this is where the electron beam gets sent back to the left-hand side of the screen by a horizontal sync pulse. And finally, once it's back on the left-hand side, it'll start drawing the left-hand border region, which again is in the background color. Only then is it ready to start displaying the next visible scan line, and it'll be back in the active region displaying pixels again. And just repeat this procedure until it gets to the bottom of the active region. Of course, then we have the bottom border of the screen, again in the background color, and inside this is the vertical sync pulse, which sends the electron beam back to the top of the screen, where it starts the top border of the screen, again in the background color. Now, we have control over all of this. In the CRT controller chip, there's a register called horizontal total, which specifies the total number of characters across the screen, which is 57 for CGA. And we have a register called vertical total, which has the total number of characters in the vertical direction. And that is set to 128 for CGA. Unfortunately, the register can't go any higher. If you go to 128, it just wraps around to 0. And so you actually don't quite get enough for a full CGA frame. The CGA monitor requires 262 scan lines, and with 2 scan lines per character, this is only going to get us to 256 at this point. So we require an extra 6 scan lines to be tacked on. And the CRT controller chip actually has a register for that. It's called the vertical total adjust register, and that's where we put the extra 6. And so we have control over that as well. And in addition to that, we can also set where the horizontal blanking region starts, normally set to 45, and we can also set the width of this, it's normally 10 wide, and we can also change the position of the vertical blanking region. It's normally starting at 112. On many chips, the width of this vertical blanking region is fixed at 16, and we can't change that. But on the Hitachi chip, you can actually change it. It turns out that the top bits of the register used to specify the horizontal sync width can actually be used to specify the vertical sync width. So that's a nice feature of the Hitachi. But basically, if we move these blanking regions about, we're also moving the sync pulse about, and so it has the effect of making the screen appear to shift left or right, or if we change this up or down. So there's a whole load of things that we can control by fiddling with these registers. The real fun of this project is going to be to figure out exactly when can we change these registers. The first thing that I've done is to write a little program to fill video RAM with a pattern, just something so we can count pixels. And actually each of these stripes is exactly a character wide, so we can count those as well. And then I've written a loop which updates the background color just briefly to red twice per frame. Now at the moment, it's not happening at exactly the same point every frame. In fact, my loop is a little short, and so it's actually updating the background color a little earlier every frame, and so it gives this appearance of sort of drifting up the screen. But no matter, I wrote my code so that I can insert additional CPU cycles in my big loop. So at first I'll add about 4 CPU cycles at a time to my loop. It's going to look like it's lost sync entirely for a while, but it should eventually start to slow down, and you can see that happening now. And yeah, that's looking pretty good. So now I'll add just 1 CPU cycle per frame and see if I can get the loop size to be exactly right so that it's always doing the background color change at exactly the same point every frame. One more, that's pretty good. Let's just add 1 more CPU cycle per frame and see what happens. And oh, look at that, it's gone back in the other direction. So what's actually going on here? Well, the CPU is reading its instructions from memory and then executing them, but unfortunately it's being interfered with because there's something else that uses the bus which the CPU needs to access memory, and that's the DMA controller. So the DMA controller is actually used for DRAM refresh on the PC. Basically, all of the memory chips in the system need to be refreshed every few milliseconds, and the DMA controller just energizes them a little bit every few milliseconds to charge up the little capacitors inside them so that they can hold their contents. And unfortunately, for 4 out of every 72 cycles, this interferes with the bus and prevents the CPU from loading instructions. So it's actually not getting its instructions in a perfectly regular way. And so what this means is that you get a lot of jitter, and it's just sort of random basically. The other thing is that I don't have an exact number of CPU cycles per frame, and so it's always going to be drifting just a little bit to the right or just a little bit to the left every frame. And so the only way I'm going to be able to fix this is to make the system completely quiet and turn DRAM refresh off entirely. But let me show you what happens if I do that. The first problem is that I need to make my loop a little bit longer now because all of those cycles that were previously being used up by the DMA controller are no longer being used up, and so I need to add additional CPU cycles to account for that. But there's a worse problem, and that is if I quit back to DOS, I get a parity check error. And this is because all those little capacitors inside the DRAM chips have discharged over time and lost their contents, and so memory is just full of garbage now. There's no DOS or anything. So the only way I'm going to be able to fix this problem is to actually do DRAM refresh myself. So let me explain how that works. These early memory chips are laid out in a two-dimensional array, and there are rows of bits and columns of bits. So if I want to access a particular bit in memory, I have to first specify which row I want. That's done using a row address. And then I have to specify which column I want using a column address. And the cool thing is that in order to energize bits of memory to do dynamic RAM refresh, I don't need to access every single bit in the memory. I just need to access every single row. And so actually, if I access any bit in that first row, the entire row will be energized. So I only really need to access each row, and there are not very many of these. It turns out that on the XT, there are only two kinds of chips that are pretty common. There's the 4164 chips, which are 64 kilobits each, and the 41256 chips, which are 256 kilobits each. And they're arranged in banks of 8, so this will be a 64 kilobyte bank, and so will this. And then we've got a couple of 256K banks. And basically, all I need to do is make sure that I'm energizing all the rows of each bank. Fortunately, Reenigne's worked out all the details for us. Apparently, the early PCs use 4116 chips. Fortunately, we don't have to deal with those because we actually don't have enough time to do that in a frame. But the 4164s range 256 by 256. So if you just access 256 bytes in a row, then that will refresh RAM if you do it every 4 milliseconds. And for the larger chips, they're 512 by 512. So just access 512 consecutive bytes. That'll energize every row. So long as you do it every 8 milliseconds, you're okay. And so this is all I need to do. I need to just break down my memory into 64 kilobyte blocks, essentially, and make sure I access 256 bytes consecutively in each of those blocks of memory in a row, and just make sure that I'm doing it in a way that will do 512 rows in the larger chips, and that'll refresh memory without actually having to have the DMA controller on. Well, there's just one more problem to solve. It seems the CPU is not fast enough to read 256 bytes from each 64 kilobyte bank of memory in my XT, of which there are 10, by the way. If you do the calculations, let's say 20 CPU cycles per byte, and I have to do this every 4 milliseconds, there's just not enough time. So I had to come up with a trick, and if you want to think about this yourself, just pause the video for the moment. What I ended up doing is, instead of reading just using ordinary CPU instructions, I had put code in those 256 byte blocks and just executed it. And this goes a lot faster because the CPU can actually read code that it's going to execute way faster than it can read code as data. And so this is how I got around this problem. Well, here's the result of that. It's perfectly still, there's no jitter, and it's doing the background color change at exactly the same point every frame. And not only that, if I go back to DOS, no parity error. It's doing the DRAM refresh perfectly. But now we have another problem to solve. Every time I restart this code, which I can do just by pressing a key, it seems to move the background color change to a different position. It's not reproducible. And the reason this is happening is because I'm starting my timing loop at the beginning of the active region, but I don't know exactly where that is. There is a register in the CGA card which flips a bit every time we go into the active region, but the problem is polling that register takes a certain number of cycles every iteration. So the first time I check that register, I might be here, the next time I check it, I might already be all the way over here. So I've really missed the start of the active region by quite a few pixels. The other problem is the CGA card itself runs on a clock that's 3 times faster than the CPU. We call the cycle of the CGA clock an H dot, and there are 16 H dots per character. There are 2 per pixel in this low resolution mode, and there are 3 H dots per CPU cycle. And so every time I start the computer up, the CGA card starts at an essentially random time, and I don't know which of the H dots within a CPU cycle it started on. And so that means that there'll be a little bit of movement due to that as well. So how do I get control of this down to the H dot? Well, it turns out it's actually possible due to a technique by Reenigne called Lockstep. The basic idea is to set up a really small CRTC frame, so 8 characters in this case, and of course we switch the monitor to blank so it doesn't interfere, and we just make one of those characters active. So there'll be 7 blank characters and 1 active character. And then we have a loop which is precisely 1 character short of a CRTC frame. So in other words, just 7 characters in length. And so every iteration of that loop, it's effectively going to be stepping back by exactly 1 character in that small CRTC frame. And I just do that until I'm in the single active character. Now, once that happens, I know I'm in one of these 16 H dots, but how do I get control down to the H dot precisely? Well, the CPU is running 3 times slower than the graphics card. If you count it out, there are 16 H dots per character, there are 8 characters. This is not a multiple of 3 H dots, so it's not an exact multiple of CPU cycles. And in fact, it's possible to set up a loop with the CPU that is 1 H dot short of a full CRTC frame. And so that means that we can just run that loop a certain number of iterations, and every time it's just going to step back by 1 H dot. And we do that until we're back out of the active region again, and then we know we're in precisely the same place every time that code is run. And now I've got my code running with Lockstep, and as you can see, it's actually doing this register write to change from red back to black again at exactly the first pixel in the active region, down to the H dot. And if I rerun this code, just press a key to make that happen, you can see it's exactly the same place every time, totally reproducible, even if I restart the machine. Not only that, I've set it up so that if I press a different key here, it'll actually step forward by 1 H dot at a time. So in other words, half a pixel at a time, which is pretty impressive. You can see that happening now. So this is what we're going to use to get precise control down to the H dot of when register writes happen to our CRT controller. And we're going to try and trick it by writing to the register just a little bit late and see if we get any interesting glitches. But in order to make this a little bit clearer to see, I'm going to switch now from this monitor over to an LCD monitor. I have an RGB to HDMI controller, and this is going to allow us to see all of this on an LCD display. Well, check it out, guys. I'll just change the pattern here so that the background color change happens on a blank scan line, and as I press my key here, and I'll just zoom in on that, you can see that it's just moving along by half a pixel at a time, or 1 H dot at a time. So I really have very fine control here. And so now I can switch over to changing a CRT controller register instead of the background color register. So let's do that. And I'm changing the horizontal displayed register here. And it looks like I'm changing it from, let's see, 9 characters down to 4 characters at a certain point. And what I'm going to do is sneak up on that change, H dot by H dot, and see if I get any interesting glitches. So let's do this. And eventually, look at that, I get a half character, which of course the CRT controller shouldn't be able to do. Now, the interesting thing about this glitch is that it doesn't happen on other CGA cards, even with the same CRT controller chip. You'll either get a full character or no character in that position. And what I think is happening here is that the CRT controller chip itself might actually be doing a glitch down to the pixel or even to the H dot, but the actual CGA card itself is only able to respond to that glitch on a half character basis. And so on the IBM CGA cards, we get a half character glitch. On the other CGA cards, they can only respond on a character by character basis, and so you really just get a single character glitch. Now, that's a little bit disappointing because my understanding is that on some other platforms, they might actually be getting glitches down to the pixel even. And that would be much better for demo effects, but at least we know now that this actually works, to some degree at least, on the IBM PC, possibly for the first time in history. So you've seen it here first on this channel. You can actually glitch this CRTC, at least on this card, to give half character glitches. Well, I've tried a few more things to find some additional glitches. So this is the normal behavior. I'm changing the horizontal displayed register from 9 down to 5 and then back up to 9 again towards the bottom of the screen. And the way it works is the internal horizontal counter counts up to whatever the current horizontal displayed value is. So if it's a 9, it'll count up to 9. When it reaches it, it starts blanking for the rest of the scan line. If it's a 5, it just outputs 5 characters and starts blanking. So this is the normal behavior. But as we saw earlier, if we go just one H dot further, one half pixel further, and set that register a little bit too late, we get an extra half character glitch. But what if I set it 2 H dots late, so one additional pixel too late? Then this happens. Now, this is not really that surprising. The value was 9 originally, and just after we reach character 5, we changed the horizontal display back to 5. So we've already passed 5, so it's not going to take effect. And it's not 9 anymore, so that's not going to interfere. So what does it do? It just keeps counting characters to the end of the scan line. And as you can see, there's a little glitch at the end of the scan line, which you can see at the left-hand side of the screen where it's wrapped around there. It doesn't display all of the last character, it just displays a half character glitch again. And that's something that this CRT controller chip seems to do. It just blanks the last half character of every scan line. You don't normally see that, of course, because that's normally in the horizontal blanking region anyway. Well, if changing the horizontal displayed register gave so many glitches, what about the vertical displayed register? That controls the number of character rows displayed in the vertical direction. And remember, there's 2 scan lines per character row, so you have to double it to get the number of scan lines. And as you can see, I'm going to change it twice per frame. Once at the top, and then I'll change it back to its original value somewhere towards the bottom of the screen there. You can see the 2 places this is going to happen. So now let me switch to visual mode so you can see what's going on. So as you can see, I've set the vertical displayed register to a value of about 7. So you get about 14 scan lines displayed. And now I'm going to sneak up on it and just change that register a little bit late, like we did with the horizontal displayed register. So if I go along H dot by H dot, we'll finally get a half character glitch again. And as far as I know, this and the other half character glitch I showed you are being shown for the first time on the IBM PC. These are not known previously, so we really have made some progress here. But wait, there's more. So if I now go along by another H dot, then it actually uses the larger value that I have the vertical displayed register set to. And you might think that's it. Now I've changed the register too late, there's no further changes. But if I actually move along h dot by h dot along that scan line, eventually it displays a full character. And then it does that for a few h dots, and then it'll display another half character glitch. And immediately on the next h dot, it goes back to the larger value again. And this pattern actually repeats all the way across the scan line, which is really curious. So again, I don't know what we would use this for in a demo, but this is definitely a new glitch for sure. Well, now I want to show you a couple of the weirdest glitches I found. The first one is a timing glitch, so it's not very visual. I'm changing horizontal displayed from 5 characters, now I'm changing it up to 8 characters. And exactly what you expect to happen happens here. So initially you see 8 characters displayed in the first scan line of that block in the middle. And that's because I'm changing the register early enough from 5 to 8, so the blanking hasn't started to take effect for 5, and so it just continues out until 8 characters. So now let me step along by 1 h dot, and you'll see that that first scan line of the block in the middle will change down to 5 characters. A little bit hard to see, so I'll switch back and forth between the two cases, and you'll see that it's changing from 8 characters to 5, and so on. Now, this is exactly what you expect. If the register is changed too late, the horizontal blanking already takes effect, and it will just start blanking from 5 characters and will just keep blanking. So no glitch here, but the interesting thing is the timing. It turns out that if you have just the right values in the register, and you're changing it to just the right value, then it'll take an additional h dot for the change to take effect. So you'd have to set the register 1 h dot earlier in that case. And the rule for when this happens is really curious. So basically, all of the binary 1s that are set in the smaller value have to also be set in the larger value. Other ones can be set as well, but so long as all those ones are, then it's going to take an additional h dot to change. Well, except for the least significant bit, that just doesn't matter, it could be anything you like. So that's a really bizarre rule, but I've checked this on other video cards with the similar Hitachi chip, and yeah, it really does seem to be a function of the chip. So if you have an explanation for this, let us know in the comments below. It's got nothing to do with the internal counter. I mean, the internal counter could be 15, and we could have 16 in the register, so that's not relevant. It's just the value that the register is changed from and to. And obviously it's down to some kind of gate delay. Some of the transistors take a little bit longer to switch on. But why this particular pattern we haven't been able to explain. Well, the next effect is probably the most interesting for me visually. So what I'm going to do is change the vertical displayed register again. I'm going to change it just before the frame starts. You can see the red bar at the top of the screen where it's going to happen. And this is going to be changed to a value of 0. And you wouldn't expect anything unusual here to happen. You just end up with a blank screen, right? Not so. Take a look at this. So yeah, it's displaying half character glitches all the way across the screen. And basically what we think is that the CRTC tries to change things on a half character basis. The clock is set to a frequency which does a full cycle every character, but of course it's changing from high to low and then back to high again every half character. And so it appears that setting blanking on or off can only happen on a half character basis. And here, for some reason, it's trying to set blanking on and off at the same time. It's trying to set it on the half characters and off on the other half characters. Yeah, really interesting effect. And I can see this being used in a demo if you had lots of frames that are all one scan line in length. You get some kind of striped effect down the screen perhaps. Now maybe that's not very interesting in graphics mode, but in text mode this could be quite interesting. So in text mode you can also set things so that there's just one scan line per character row. So I don't know about you, but I'm keen to try out some of this stuff in text mode. Well, here's 40 column text mode, and actually you can see that the half character glitch is happening here. So if I go back, it disappears, forward 1H dot, there it is, and of course we get the glitch all the way to the end of the line if we go one more H dot. So it looks like, at least in the 40 column modes, text and graphics, the effect is exactly the same. But in the 80 column mode, I wasn't able to find any glitches at all so far, which is really surprising, especially given that in the 80 column text mode you get a lot of snow if you try to write to video RAM. That's one downside of the IBM card. I don't know how well this is going to show up on camera here. What you're looking at is the 80 column text mode, and along the top here are some red marks, and down the bottom some black marks. And believe it or not, what you're looking at is snow. Now these IBM CGA cards are absolutely notorious for this in the 80 column text mode. If you try to write to video RAM or read from it, you'll get snow all over the screen. It's usually completely random and flickery and so on. But here we've actually managed to freeze the snow in place. And we've done that by writing to video RAM in both locations and also reading from it down here in exactly the same point every frame. So we're not actually changing these locations in video RAM. The locations I'm changing are actually up here in the left, and that's why you can see there's a little bit of a black block there. Up the top here, I first change these to red characters, and then down the bottom I change them back to black again. So by the time the electron beam gets around to here, it just has black in that location, and so that's what you see. So these characters here are the actual snow characters that you get because the card gets confused. When the CPU tries to write to these locations up here, it has to set the address that it's writing to the correct address for these places. But at the same time, it's trying to read the characters that are in video RAM that correspond to these locations. But it's trying to do it at a time when the address is currently incorrect, and so you get something wrong on the screen. And so this is really cool. I don't think that this has been on YouTube before. I think Reenigne has done experiments along these lines, but this is probably another first on video. And basically what we're doing here is writing some red characters, and the snow itself at the top here is red. And what this shows is that the attribute of the snow character is actually whatever you're writing into video RAM. It doesn't even need to be an attribute that you're writing, just whatever value is written into video RAM is used as the attribute of the snow. And what the character of the snow is comes from what you're overriding in video RAM, so what was there before. And likewise down here, I'm writing black characters into video RAM and then reading them again, and actually the snow characters, the character and attribute comes from what was already in video RAM, the value that you're reading. So now we actually know what snow is precisely, and we can really control it, as you can see, down to a very, very fine level. Unfortunately, the only way to get snow is to either read or write to video RAM, which is very slow, and so there are big gaps between the snow characters, and that could be sped up a little bit, but then we'd lose a little bit of control over what we're writing. So it turns out that this is probably not that useful in an effect. You can make it so that the snow characters are exactly equally spaced across the screen, but it's a fairly big gap between each of the snow characters. So I can't really see this being used in an effect, at least not in a really impressive way for a demo, but maybe someone will come up with something one day. But I just thought it was really cool that we can actually now control snow and freeze it in place on the screen and work out exactly what it is. Well, there are some glitches that I didn't show you, but that's because they're already well known, and I've actually got videos on my PC Retro Programmer website about this already. So the truth be told, there's still way more that could be done. There's so many video modes and so many tricks that you can play with the CRTC. And it's taken me weeks to write all the code so far. But if I come across anything interesting, I'll be sure to include it in a later video. And it's really hard to balance the content, which is really quite technical in this case, with making a video that's entertaining to watch. So I hope I haven't bored you all completely to tears here. But if I have, don't worry, we've got some really interesting hardware videos coming up. I've got hold of some extremely interesting video cards, and I'll leave that for the next video. So until then, see you later. Bye.